Good evening. Welcome to the second program in our webinar series, NASA Aeronautics, Aviation at the Leading Edge. I'm Suzanne Smith, the Director of the Kentucky Space Grant Program and the Director of the University of Kentucky's Unmanned Systems Research Consortium and a Professor of Mechanical Engineering. NASA's Space Grant Program has consortia of universities and other partners in each state, plus Puerto Rico and the District of Columbia. And we're all focused on STEM education, workforce development, and aerospace research, inspired by the exciting work of NASA's mission directorates. First, I want to thank Old Dominion University for hosting this webinar series and their fantastic facilities, and the Virginia Space Grant Consortium for coordinating these programs with NASA. Yes, we're called Space Grant, but we have members across the nation who work on aeronautics and aviation-related challenges. So for this series, we're focusing on the first A in NASA, aeronautics, the study of the science of flight. NASA has made decades of contributions to aviation, safe and sustainable, by reducing emissions, noise, and fuel consumption while enhancing safety in the national airspace. NASA-developed technology is on board literally every commercial aircraft and at every commercial airport in the U.S. We've partnered with NASA Aeronautics Research Mission Directorate to introduce you to the people, ideas, and technology driving the ongoing transformation of aviation. So tonight, we'll look at urban air mobility, an emerging technology for future transportation in densely populated areas that leverages recent R&D for a system to enable safe flight for drones. And we'll be answering questions. After our main presentation, to submit a question, use the chat feature on the webpage at any time during the broadcast. Please include your first name, your major, and your university. First, welcome to Star Ginn, lead for NASA's Urban Air Mobility, a grand challenge at NASA's Armstrong Flight Research Center in Edwards, California, and Jeff Hamola, integration and testing lead for Unmanned Aircraft Systems Traffic Management at NASA Ames Research Center at Moffett Field, California.
Good evening. Thanks for having us.
Yeah, thank you.
So where are you each originally from, and where did you go to university?
So I originally grew up in Massachusetts. I bounced around a little bit before that as a son of a career Navy sailor. So we bounced around to San Diego, Japan, Florida, and then after that to Massachusetts. So kind of grew up there. After that, went into the Navy myself for a number of years, 8.5 years. And got out, and I originally went to school in Monterey, so Monterey, California, at Monterey Peninsula College, and then from there went to UCLA, where I got a degree in cognitive science with a specialization in computing, and then a graduate degree in human factors from San Jose State University.
Wow, Star?
Yeah, so I grew up in Southern California, Ventura County area for half my life, and then for high school we moved up to Palmdale, Lancaster area, where is the mecca of aerospace flight testing. And then I went to Cal State Northridge and did my mechanical engineering degree. And then after a couple of years of being in school, figured out that I wanted to go back and do a master's for the specific work I happened to be doing at NASA. So I went to UCLA and got a degree in aeroelasticity, a master's.
Well, to introduce our topic, tonight we're going to have a short NASA video. So let's start. Let's open up the skies. To be honest, what immediately comes to mind for me with urban air mobility is the Jetsons. I'm that generation. But seeing this video, it seems really different than that. How do I match my expectation with reality?
Yeah, so the Jetsons was kind of an idea of a car comes and gets you at your house and takes you where you need to go, and there's these lanes in the highway. I think where this is going to start out is going to be more like a scheduled, like a shuttle or a metro. So they call it Air Metro. Then we'll move on to maybe more on-demand type of, still some designated routes, but the timing isn't just scheduled, it's more when you need it. There's business models where there's emergency capabilities where you're saving lives or search and rescue. There's also people who are looking at tourism. Those are very safe routes. There's one in, one out of those routes. They're scheduled, and so there's some people looking at, I'm going to make that pilotless as my first business model. So just anything that you would need an automobile for, you're going to be able to see this, like get out of traffic, get up in the sky.
Yeah, and I think if you go back, especially to like the intro for the Jetsons, if you can look it up somewhere, there's really a flexibility to that notion and the way that airspace looks in there, and that's really kind of reflects the dynamic nature that we're trying to enable through our different projects that we're working on right now.
So I understand that urban air mobility is going to leverage the UAS Traffic Management system as a starting point. I saw on the NASA website, which is one of the Learn More reference links, that there were lots of phases of testing that each built on the previous phase. Jeff, can you tell us about these and how the technologies perform?
Sure. So I guess if we refer to the background here, it kind of reflects a little bit what we've been doing so far. So we've been doing a lot of testing in the UAS Traffic Management, or UTM project so far. This image in the background is a snapshot from the testing that we wrapped up in the summer. But that was kind of the end of a long path towards where we got today through a lot of testing with industry partners and working closely with the FAA and other organizations. So the project itself started formally in 2015 at NASA, and that kind of, before that though, there's a lot of conversation that kind of led to where we are today. And the impetus for those early discussions was that, all the forecasts looking at the use and demand for small UAS for commercial applications in particular, the demand was, exponential, the growth over the years. And so a lot of companies looking to start using them, leveraging the kind of capabilities for small UAS to do really a number of different types of use cases. So package deliveries is one that we hear about a lot, but there's also, real estate, agriculture, search and rescue, like Star mentioned, emergency services. So really a whole, a wide swath of possibilities that these types of vehicles enable. And so, we need a system that can help accommodate all these different use cases and business models from different companies. And so that's where kind of UTM came to fruition, where, the new entrants that wanted access to the airspace needed the flexibility to be able to access the airspace in an equitable way. And then there are current users, not at the scales that we imagine, but current users of the airspace want to maintain their access, but also have it be done in a safe way. So this is, coming in from an aviation domain. So the safety is really key to enabling all of this. And we are trying to carry forward decades of research that we've done at NASA and Aeronautics, where safety has been at the core of all of that. So this is really kind of living on into UTM.
You have some slides?
Yes.
You're going to show us?
Yes. And so, why is UTM needed? This basically kind of this demand that I mentioned. And so that kind of fed into being able to accommodate all these use cases, and then being able to allow these new entrants and current users that are operating today. And so, UTM is basically like a parallel or complementary approach to air traffic management. And so today we have a current air traffic control system, a national airspace system that is very safe, and but what we're looking at in UTM doesn't necessarily map to the traditional way that air traffic is controlled or airspace is managed. And so UTM as an ecosystem is going to enable this distributed, automated approach to being able to scale efficiently, equitably, and safely for these new use cases. And so we're working really closely with industry and the FAA. So we're looking at industry to drive the innovation and use their technological prowess to kind of drive where UTM goes as a kind of on the commercial aspect of it. But it's really important that the FAA maintains their regulatory and operational authority of the airspace as well. So we have to, as part of this research, understanding kind of both sides and making sure we're walking in lockstep together as we move forward. And so through the development of UTM, we're trying to enable this really large-scale, kind of eventually high-density types of operations that allow for multiple beyond visual line of sight types of operations, looking at defining the roles and responsibilities for all the different stakeholders, and defining, through this process, we've defined information architecture and data exchanges that are needed for this new kind of system that's going to enable these new use cases and operational types. And then what are the performance requirements that are going to be needed to be able to operate in this new environment? So here's a little bit video clip that kind of shows things at a higher conceptual level. So we have the traditional national airspace system, which is very safe. Air traffic controllers are talking to each and every one of those aircraft. Here's general aviation at some of the lower altitudes and uncontrolled airspace, but it's still really considered part of the traditional airspace that we normally think of. And then when we start looking at kind of more suburban and different types of environments with different use cases for all these different operations, kind of doing everything all together, it's going to require a lot of situation awareness, exchanges of data for all the operators to know about each other. And this is really what leverages kind of the research we've done to allow for that exchange of information and management of that traffic. So here's all those operations operating together, all in the same area, and in these kind of protected operation volumes where we kind of know the intent for where the operators want to go. They're reporting their positions. The UTM ecosystem is monitoring their conformance to their trajectories and their overall operation plans. That was an example of agricultural application, and here we're at the more urban types of environments where you need kind of tighter operation volumes to allow that scalability. And then, it's really important for all the airspace users to know about the different constraints in the system and airspace classes and airports to be able to kind of avoid those safety critical areas. So that's really an important piece for UTM to be able to allow for that situation awareness and exchange of information so that all the operators are able to be on the same page and operate together. And so the way we've kind of approached the research within UTM was to define 4 different what we call technical capability levels, or TCLs. And each of these TCLs kind of built upon the previous one, where the risk and complexity for these environments kind of progressed as you move from like TCL1 into TCL4. So TCL1 started back in 2015, and it was kind of part of this crawl, walk, run approach that we've taken. So it was kind of a more simple environment, remote types of applications, rural applications in agriculture, where we had industry come out to one of the test sites and do kind of our initial connectivity checks. They flew, but we could actually access their information and see how all of that flowed through that architecture at the time. And then we progressively moved through the different TCLs, kind of adding more density, more complexity to the types of operations and interactions between the vehicles. And then in TCL4, which we just wrapped up this summer, we were looking at high-density operations in urban environments. And so we were in actual downtown environments in Reno, Nevada, and Corpus Christi, Texas. And we were looking at beyond visual line of sight operations in these environments, looking at contingency management and public safety applications as well. So here's some clips from what we were looking at going into it. So this is a view of the planned operations that we were looking at for the downtown Reno environment. And this is kind of gets at some of the simulation capabilities that we have. So before we go out and test, we do a lot of simulations where we can visualize and understand the interactions of the planned operations. So here's a number of operation volumes supporting 5 different operations downtown. They're all strategically separated. And for this testing, we were looking at kind of remote landings, remote launches, all in the presence of buildings, downtown environment that has impacts on connectivity, communication, and navigation, and then looking at how we can all operate together, but being able to access landing spots and do contingency management procedures. And so that was kind of leading into the testing, and then we actually, back in August and July of this year, actually went out to the different sites and started operating with all the partners. So we had a number of industry partners that developed their software and flight crews out there that were flying in the UTM ecosystem. So you can see some of these taking off from rooftops in downtown Nevada. You can see how close they were to buildings, and this is was important for us to understand kind of the flight planning process and the impacts to the ability for communication and navigation impacts, and looking at other areas kind of for data exchange, as well as sense and avoid, and kind of these encounters between vehicles. So we wanted to get vehicles in close proximity to each other, have them be able to operate in that close environment. And this really is all kind of facilitated by that architecture that we've developed in UTM so far. And then this was in Corpus Christi, and this really gets at kind of an important piece for us where we want to understand public safety's, their role in this and how they can integrate into an airspace that has a lot of other commercial operators. And so here's just another piece from Corpus Christi where we had, again, similar to Reno, vehicles getting close to each other and making sure that we're monitoring at the same time. The UTM system is able to monitor these operations and maintain that level of safety that's required. And so going forward, the impact of our UTM research is being kind of felt as we're going out from here. So we're really proud that we're looking at fielded systems. UTM did not exist prior to NASA involvement, so this really kind of came from our efforts here at NASA to really enable a new industry. And so you can look at already fielded systems, like Lance is a direct descendant from our NASA UTM research that the FAA is using right now to enable operations near airports. And we're feeding into rulemaking, so the research and the results that we're coming up with are feeding directly into kind of these new rules and potential policy decisions that are going to impact areas like remote identification and operational approvals. And then industry guidance is where a lot of what we're doing here, working closely with industry, and so this is going to feed into their where they go from here as UTM kind of takes shape and becomes really a new industry. And it's going to be standards development is part of that process as well. So we're kind of giving direct information into these standards bodies and participating in the different groups that are kind of standing up and establishing these new standards. And then there's international harmonization. So that's another area we're proud of, that we kind of started it here. It came from NASA in the US, and it's spreading into other areas in Europe and Asia that are kind of following our suit in UTM and standing up similar concepts and constructs.
Wow, UAS Traffic Management is really complex when you hear all about all the different aspects of it. What's next for UTM?
So at the project level, this is kind of a closeout year for us. So we're kind of wrapping up some of the analysis and reporting, and we're going to be handing over our research transition products to the FAA, and then they're going to carry it forward in their series of tests. And then, so we focused in UTM on small UAS in the lower altitudes, but that's also, you can consider that as part of a crawl, walk, run approach to a more general paradigm shift in air traffic or airspace management. And so we never meant for it to be limited to only that area for UTM. So the idea is that it can be applied elsewhere, and that's where we're looking at now, how UTM can be leveraged and extended to support, like urban air mobility. And that's where we're looking at now with, UAM and the Grand Challenge as well.
And Starra, that brings us to your work for the Grand Challenge for Urban Air Mobility. First of all, why is this called a challenge?
Yes, so we have a background here that shows we're trying to put passenger carrying vehicles now that have maybe more automation to them in these dense urban environments. But the difference is we're integrating with all of the rest of the national airspace there. And so the challenge for us is to kind of build the Grand Challenge as a conduit to build a safety case around the whole system of pilot training, vehicle safety, airspace management, and not only how we take an extension of this UTM, but how do we communicate with the rest of the national airspace that's out there right now. So besides the picture behind me, on my first slide here, this shows there's lots of different business models for UAM. We'd mentioned some of those at the beginning, but as you can see, some of those operations can get tight. Weather in around these buildings can be quite difficult to land in. So there's lots of different aspects of the project we're trying to consider from a system-wide perspective. So we coined the term urban air mobility, UAM maturity levels, just like technology readiness levels, but it's at a system level. So this is showing right now we're at a UML 0. There are no certified vehicles right now. Anybody who did certify a vehicle at this point is just going to abide by the current rules that are in the national airspace. And so by collecting data early with the Grand Challenge, we're able to start informing, bringing data to the FAA to help them kind of collate and figure out what in the standards needs to change, what are the gaps, so that some things we'll still be able to leverage, some things will change because these are distributed electric propulsion airplanes, so they're new technologies, they're all fly-by-wire, they have a lot of automation to take some of the pilot functions away, and so just the training and certification of those things takes some time. But what's really important for the vehicle companies is the market studies say that if this is going to be a viable industry where all of us get to pay for a seat on one of these air taxis, then you're going to have to mass produce these. And that means the airspace is going to become very dense, and you're going to have vehicles that fly a lot closer to each other in coordinated fashions, and something maybe that looks similar to what Jeff showed you. And so as our UMLs, as we do each series of the Grand Challenge, we're trying to identify what the requirements for any kind of rule changing needs to be to get to these higher density, more complex operations, but constantly making sure it's as safe as our national airspace is right now. So the Grand Challenge will go through to determine requirements at a UML 4 level, and that time frame for where we set requirements is about 2026. And again, that's not to say we're going to be operating at a UML of 4 in 2026, but we know what needs to get in place to do that. So the Grand Challenge has a lot of things that it's going to affect. We have developmental testing that's going to be this next summer, and that's what we're calling our design of experiments, where we're trying to understand the right range requirements, how we need to assess the safety of the vehicles, understand how we're going to do the two-way network with piloted vehicles, and let machine-to-machine communication help you through like your flight path. We'll be figuring out some of the challenges with weather, and we'll have some weather measurements. We're going to be doing noise measurements of the vehicles. Noise is an important piece of getting public acceptance in these vehicles. So right now you don't see helicopters anymore flying around in urban airspace because they're too loud. So these definitely have to be a lot quieter because they want to be in and around the urban environment. So as we're doing each step of the Grand Challenge series, the other cool benefit is as we find things that work, or safety cases that industry brings that works, and then we can help feed that to the FAA, that's great, that's near-term benefits. But the things we find gaps in, the technologies or capabilities that still need to be developed, now we hand those off to our NASA research projects, and they can take some more high risk and buy down some of that risk, before industry is ready to do that. So the series will go out, again, four different times. We have contingencies that we're going to look at. These are the same contingencies that just anybody who gets their pilot's license has to understand how to operate. But we break this down in the fact that we're going to have less human functions thinking through these contingencies and more machines thinking through these contingencies. Now, I'm not saying like artificial intelligence necessarily right away, but there'll be scripted, pre-programmed, autopilot kind of routes. But how does the decision making happen when you have an air-to-air problem, or you have a balked landing, or you have a missed approach. Those all affect the distribution of the air traffic. So you have machines that are trying to manage that air traffic. You have ATC that has current people they're trying to manage, and somehow those two systems have to connect to each other. The other thing we're trying to figure out is what's the reserves for these vehicles. A lot of them are going to be all electric. They have maybe 45 minutes to an hour of flight time. Today, you have to have 20 minutes of reserves, and so they don't want to have 20 minutes reserves. So we're trying to figure out what do we fit in their necessary payload of positive energy versus a contingency comes up and maybe they got to go at least 2 miles or something like that. So we're breaking down the airspace, but we're looking a lot about the dynamics of air traffic and performance of the vehicle at the terminal area. So there's calculations behind every piece of the route that we're flying. I never realized the airspace is broken down into like trigonometry and specific things, but they're all based on the performance of the vehicle. And so right now they're based on either fixed wing vehicles or helicopters in these terminal areas, or the transport airplanes. And the performance of these vehicles, although they're landing vertically, they really want to fly straight and level like a fixed wing airplane. So we're still trying to figure out how the performance is going to change in the vehicles. So we've been putting together animations as we can explain this into our teams. There's going to be this flight planning that happens with the machines. They're going to show that they can fly different kinds of crosswinds. We also have some research for looking at simple vehicle operations, which is how do we pull away, automate some of these pilot functions and make it very easy to fly these airplanes, like you would only need a driver's license to fly them. So this is actually a real cockpit flight simulator out at NASA Ames. And then we're trying to show you back and forth between, as we're flying in the Grand Challenge, the pilots will be flying in a simulated urban environment. We'll pick whichever kind of airspace use case that our participants want to see. But we'll simulate that around the desert this first time just to figure out the experiment. And then the pilots' cues, they'll have cues that are coming from machines. We'll also have normal voice commands because we will be entering the national airspace right away. But flight path changes, approach and landings, they don't want to, in a helicopter route, there's a lot of times you have to hold and wait for traffic because you're the lowest priority in routing people because you can actually stop and hover. But these vehicles certainly don't want to do that. And stopping and hovering in these vehicles is like exponential drain on their battery. And we're trying to, infrastructure is a big piece of what we're trying to figure out. So how well can they control that vehicle? How large do the heliports have to be? It's going to be different than helicopters because it's defined by like your rotor blade diameter, and a lot of these are winged with little propellers. So infrastructure, again, pilot workload, what do we need to understand? What's interesting is in these flight simulators, if you actually put somebody in there that is a pilot, it's actually harder for them to land this than we had. Like we had one of our mechanics come in and fly it, and he's never flown an airplane, and he landed it way better than everybody else. So it's interesting. It's almost like you're trying to find that gaming environment. How would they fly an airplane, and translating that into here. There's other research that NASA's working on to automate those pilot functions, not just from how easy it is to control it, but like some of the outer loop decision making of contingencies that come up, and what's alternative solutions, and how do I make a decision on the thing that costs the most damage versus the next thing that costs the least amount of damage. And so a lot of very interesting research there. So the research not only will build some of our research in automation, more research, and we have an air traffic management research project. We'll probably find some gaps in some of the technologies on the vehicle as far as reliability, dependability. So we can feed that back to those research projects. And obviously we've been working with the FAA is a very close partner in this with us. We've been working with them to formulate the Grand Challenge for the last year. They've been helping us determine what some of those equations are and measurements that we have to take. And so we have both. We have air certification, we have flight standards, and we have the ATO. And underneath all of those are multiple lines of business. So right now we're breaking down these scenarios and scripting them out. And then we'll have participant with the Grand Challenge just officially started October 10th when our public announcement came out. And so we're waiting for applicants to sign up with us by the end of December. And then we'll start tailoring what they need for the Grand Challenge. So we're really excited.
For those of us who spend a lot of time on the road, we don't do as much contingency planning as you're talking about. And I know that's a big part of pilots that fly in the national airspace. It's really interesting how much challenge that adds to the whole system, you know, to be able to blend both of those aspects.
Right. And right now, I mean, the rules for unmanned vehicles is they have pre-programmed contingency. So if they know a route is going to be 20 miles, they know every spot that they can possibly land on that route. And it's just a matter of them knowing which one they're the closest to, and then that program will go back in. Or if they lose communication with ground, they know that they go in a loiter pattern, wait till they get a signal again. Otherwise, they just know they're going to go back where they started and land. So you might see you'll see those safety nets always in this stuff. But I mean, as automation, like in 20 years, starts getting smarter, and we do get to leverage the artificial intelligence, be more dynamic decision making probably.
So for our audience, this is a final reminder to submit your questions using the chat feature in your webpage. And please include your first name, your major, and your university. So while we're waiting for those to come in, could you tell us more about your career journey? Jeff, let's start with you.
Sure. So actually, when I was in graduate school is when I started an internship at NASA Ames, and so I got into the research lab where I'm in now, the Airspace Operations Laboratory, which has a lot of great people in there. And I started as an intern, kind of going to class at night, and then kind of being part of the lab during the day, participating in the research that we did back then. And after I finished my thesis at school, I was able to actually leverage one of the research projects to use as part of my thesis, which was very fortunate and exciting to work on, to kind of bring the two, education and work together. After I finished that, I got hired on as a contractor through San Jose State, and was a contractor for a number of years as one of the researchers in the lab, and then eventually converted over to being a civil servant. So kind of got to see the different aspects of life at NASA, and all the different players and the people in the different roles are really, really important, and we're all really part of one nice, good team together.
And Star, I think your path was a little bit different. What about your career journey?
Yeah, it's hard to talk about a career journey with not including your internship right there, because really that defines that career path, right?
Yeah.
I mean, I think it's so important to get involved in those internships so that you really do pick that thing that you're passionate about working on.
But your first internship was when you
My first internship was when I was 17.
High school?
In high school, yeah. And so they picked one student from every high school in the Antelope Valley where I lived, and they said you get to work 6 weeks as an engineering intern with, it's like you walked into the Right Stuff movie, right? Test pilots walking around, they're movie stars, and you have SR-71s, and you have F-18s and F-16s and X-31. I mean, all the latest and greatest things that most people in the world just don't even know is happening out there. And it was just like love at first sight. So I knew right then I was going to be a mechanical engineer. So, I already mentioned the colleges I went to. But when I started my career, I actually started in an area that wasn't necessarily mechanical engineering, because that's just the position that they had. And it was structural dynamics. So I did a lot of on-the-job training and learning, which I really realized that school is kind of there to help you learn how to solve problems and what reference material you need to go to. But really, everything's on the job. It's very non-linear in the world of aerodynamics and how everything works. So I went back. That's when I went back to my master's. But I did that structural dynamics for 10 years, and then I was the branch chief for the aerostructures branch, which my group was in. And then after I did the branch chief job, then I went in to be like the chief engineer of all of our aeronautics research at the center, which meant I was trying to figure out what is the strategy for the center, how do we engage into that mission, the Aero Mission Directorate. So I did that for a while, which meant working with all the technical people that had different ideas about this electric propulsion per se. That was like really my biggest motivation, was getting us to start doing electric propulsion. And And then I was a director of research, and
Wow.
then or deputy director of research. It's hard to say those. But then now I'm doing this UAM Grand Challenge. So it was like this great, starting from the beginning of this industry to now helping enable like a huge ecosystem in this industry.
Well, and that was the next thing I was going to ask. It's obvious you both love what you do. So what one thing do you love about what you do for these students out here?
You and good.
Yeah, so I think being able to participate in UTM as it's kind of in the very early days, and really seeing it kind of come through, to its fruition has been a really exciting thing for me, and a feeling of accomplishment of being able to be engaged in that and kind of see where it's going from here, and really, having a stake in where it goes from here. So we've really enabled a new industry, and it has a tremendous potential just out, not only within that scope within itself, but beyond that, like I mentioned before, just internationally and other types of airspace and vehicles. And so it's really exciting to have, be a part of it, something I can point to.
And Star?
Yeah, same thing. I mean, at NASA, they're starting stuff at this ground zero, but they don't all work out, right? I mean, our job is to do high risk research and buy down risk for industry. But when you do get to work on a project that you were there, the advocate or the brainchild at the beginning, and then you actually see it grow into $1 billion industry. I started working with the other centers of advocating electric airplanes, and we were able to do some experiments very fast with small businesses to show that there was a validation to the research. And then we were able to, pitch to headquarters that we should do X-57, which is NASA's first electric airplane. And so that's just been going on. And I mean, that's just a piece of now this urban air mobility. They're helping with certification of the components of the airplane. And now we're working, to develop the airspace and how those are going to interact in national airspace. So it's just amazing to have this opportunity.
You love everything about it.
Everything.
Everything about it. So what advice then would you give today's aspiring engineers, technologists, programmers, designers, all of the different disciplines that are involved?
Yeah, I think that's, to kind of keep an open mind to your education and your potential paths outside of where you are now. So, like we've discussed so far, there's really so many different pieces to these new systems and these new vehicles, and it's going to take very kind of different skill set, different mindset, and I think it's going to just take people coming from any background is going to apply to these new concepts. So whether it's traditional STEM or even if it's graphic design, we have to be able to communicate these new concepts out to the public, because it's pretty technical, but these have societal impacts, and so kind of drawing on multiple disciplines and just not limiting yourself to one particular path, but kind of keeping it open for yourself and taking every opportunity you have to learn something new.
What about you, Star? What advice would you give?
Yeah, it's I think everything is so multidisciplinary in this new technology area. So we've made the performance of individual technologies, we've advanced them as far as we can, and to make any more advances in aircraft right now, you're looking at multidisciplinary. So it was very clear to me in these last 5 years with a couple of different projects. We had controlled flexible structures, and now we have X-57, but the disciplined engineers need to be able to talk each other's language to design an airplane now. And so you can't just know structures, or you can't just know controls, or you can't just know electrical engineering, because the aircraft design guys need to be able to speak electrical engineering, and vice versa with you. So really having more of a breadth and being bilingual, trilingual now as you're doing your studies, I think would be the greatest benefit to where we are in aviation right now.
Yeah, trilingual, I like that. I'll have to remember that for my classes. So how were your internship experiences important to you? And have you had any interns that you worked with?
Yes. So like I mentioned, I started as an intern, so that was a kind of important formative period for me, as kind of learning how this research is done, what are the expectations are. And it was interesting, kind of challenging, because before that I was in the Navy, so kind of coming from that mindset into a research environment was quite a change for me. So that internship gave me that sort of gentle introduction where I had a lot of great mentors that followed me through the process. And then I've tried to carry that on today with interns that we get kind of in the summer. We also have interns kind of throughout the year as well. So I'm trying to kind of carry forward that experience that I had.
For me, I think interning is really important because it lets you try out different kinds of areas of engineering. So I did aerodynamics, and I did controls, and I did integrated systems. I was a flight test engineer, so I actually got to fly in an F-18 2 times, which was probably a highlight of my career. And so, yeah, I mean, now you know when you're graduating, like this is the specialty or area that really excites me, or once I want to get into. So having that knowledge.
Great. All right, now we're going to go to our questions that have come in online. And I have a list here. The first one I've got is from Markian. His major or her major is Aerospace Engineering from the University of Alabama. And this question is, how will the system change as the technology used to detect and track these vehicles evolves?
Yeah, I think, well, throughout the evolution of UTM, as we've been doing the research, we kind of settled in on an architecture that's kind of been pretty stable for the last few years of the research. And so I don't know how much the system itself will change, like the fundamental pieces of it, but the idea is that this architecture and this system, ecosystem that we've developed so far is going to be extendable and scalable to incorporate new types of services, new other systems that'll kind of feed into the overall ecosystem and ability for us to scale to the operations that are needed. And so I'm not sure how much it'll change, but we've tried to set it up in a way that it can adapt to and accommodate any changes and innovations that come afterwards. So there'll be changes, but I think the fundamental pieces will hopefully stay the same.
Let's see. Star, I think you mentioned something related to this before from Christopher, who's majoring in biosystems engineering at the University of Kentucky. How will you manage flight plans with variable weather?
So right now all flight plans are done through forecasting. For the initial market for these vehicles are going to be a short distance. So forecasting what's going to happen 15 minutes from now probably isn't so hard, but I think we will need to get to real 4D trajectories with real-time weather sensors. So we have, like for the Grand Challenge, we have an array of weather sensors, and we're trying to figure out, what is the right way to communicate a 4-dimensional space of weather for how you need to land on the vertipad for those, flight safety kind of things. And then so you can update your schedule, through the route. 15-minute routes is probably not going to be off too much. And hopefully they are not as affected by winds as the smalls can actually push them around and change their flight plans. But it is definitely one of the pieces that is part of the project.
So in addition to, engineers and all the other pieces that we think about, communications, there's also meteorology and all kinds of other dimensions of this for the future. So Hamza, who's majoring in aerospace from the Georgia Institute of Technology, says, what's the single major challenge in developing new FAA regulations for these mobility systems?
What's the challenges? Well, I mean,
FAA regulations.
Right. So we had there's plenty of historical data of people, developing new, like Honda Jet, came up with a new jet, and that was a long time to do the research, and then you get done with the research, and then you make sure you're operational, and now you got to collect a lot of empirical data for the FAA. So we all know what the process takes, and we know how long that process takes, and I can't imagine why something would change in how fast we can do this. I think it's going to be a little bit harder because these have a lot of new technologies on them that don't have a lot of empirical data behind them for reliability. But if there's as many as we think they're going to be, like right now there's 200 designs on paper, and people are at different phases of building those airplanes, and we're going to be able to collect a lot of data at a lot of time. We're not trying to change the national airspace, right? But we're trying to add to it safely. Even making changes like that can be a 10-year period. So, I would see doing some low dense operations in urban environments definitely past 10 years, where somebody's paying for a seat in that airplane. But you'll see these airplanes flying around earlier than that as they're getting their operational experience.
Yeah, I think that you said the certification process for these are new types of vehicles that haven't flown before, new aircraft, new components in there. How do they integrate into this airspace system that's being developed as well? So there's a lot of kind of challenges up ahead, but I think, like you mentioned before, the FAA has been very closely aligned with us or working with us all throughout each of these projects right now. And so it's a good sign that we're kind of converging and marching towards the same goal at the end of this.
So Kayla, who's majoring in aerospace engineering from the University of Alabama, says, would there be a noise threshold that would be part of implementing the urban air mobility in the urban airspace?
Of course. I mean, right now there's curfews for airplanes around current airports, and they have regulations for what their noise level can be. What's interesting about this, it's not that we can just go in and say, like, well, if these airplanes have this noise, then you're fine. You can have that. You should just be able to meet that noise. But it's the perception of that noise is going to be different because it's 12 spinning propellers, and although the dB level can be lower for those kinds of vehicles, the frequency is higher. So there becomes maybe like an annoyance. So if you can, the previous series, this webinar, they talked a lot about noise. Obviously, it's low boom, but there will have to be a similar thing where you do all these community kind of outreaches as part of the research of what you're doing, and do surveys and make sure that you can understand how the noise changes, or you can point the noise away from a community versus busy freeway or something. And if you can start directionalizing the noise, there's definitely research being done like that.
So there's the noise and the perception of the noise that both have to be dealt with.
Right.
Yeah, so actually within TCL Forward, when we were doing that testing, we had a number of human factors researchers that were deployed out to the test sites to do this kind of community engagement and do surveys with the public to start getting at some of these questions as, what is the public perception of these visual noise versus, oral noise. And, that kind of feeds into eventually what are the potential thresholds and where they might be and which environments you need them in.
Yeah, that gets back to another discipline, human factors, right? And the study of humans, which is really complicated.
So Linda now is in physics and astronomy at Minnesota State University, Moorhead, and it says, we're wondering how the presenter got into aeroelastics in her studies and what led you to this field. So I guess that's for you, Star.
Yeah, well, so this gets back to, usually I'll tell the interns that maybe you don't want to just jump into your master's until you find out what job you're actually going to get. So although I had interned at NASA for 7 summers in a row and thought I could kind of pick my job, well, it wasn't that easy. There was so many slots and so many branches. So they actually said, well, if you want to work here full time, you're going to work in structural dynamics. And we study aeroelasticity here, and I hadn't even taken vibrations in college. So it was a little overwhelming. But again, a lot of on-the-job training. Then I thought, hey, this is a good area to go back and get my master's in, so I just understand the fundamental theory. But it was so difficult. They call it a black art. You can't actually calculate everything about it because there's a lot of nonlinearities in it. And so there is some gut feel to what you do in aeroelasticity. And that was great because usually if you're in a review, nobody knew how to question you whether you knew what you're talking about or not because it's a black art. But yeah, I really enjoyed it. I mean, I'm glad I ended up there. Everything happens for a reason.
Matt is majoring in mechanical and aerospace engineering at West Virginia University, and he says, who's the target customer for urban air mobility?
Well, if you're gonna, the target customer is everybody. It's supposed to be the people that can afford just to get it like an Uber are the same people that can afford this. They, at the starting costs, right now there's $2 to $3 billion being invested into this field right now, and it's all small businesses being funded by venture capitalists, and so everybody sees there's a market in this for the masses, and $2 to $3 billion a year should say something about that. As anything starts, like the first time electric cars came out, they were pretty expensive when they first came out, and now I lost count how many Teslas I see on the freeway. Then they got the cost down and understand how to develop the technologies faster and cheaper, and but safe, right? So so yeah, it is for everybody.
Yeah. It's not only for passengers. These new vehicles can do larger transport operations as well. So it's not only for people going from one place to another, but it's also the transfer of goods and these public safety use cases as well. So
yeah, you mentioned emergency response before.
Yeah, right.
So that's another part of it. I've got AJ here, a major in aviation management from San Jose State University. And it says, one of the challenges I see is public acceptance. How do you get the public to accept the noise and traffic from these vehicles? And with regards to urban air mobility, UAM, how do you get people to sit in a vehicle that is piloted by someone who's not as experienced as a commercial pilot?
So I'll start off and just kind of dovetail off of what I was mentioning before, where we sent people out to kind of engage with the public to start understanding where their concerns are and where some of these issues are with noise and privacy and those types of concerns. We also engage, have people come into our lab as well, and kind of we walk through use cases with them to get at these similar concerns. So looking at a system that's transparent, that gives them the information they need about what's going on outside of your house or downtown. So it's really important for us to engage with the public as much as possible to start getting at these acceptance issues and seeing where how that feedback and those decisions can guide where we go with UTM and UAM.
So this question I ask everybody when I'm in a public forum, and I said, would you get? Actually, I just say, would you get in a driverless car? I just start there. I don't even start with the airplane one, and it's different. The perspectives. It's like, well, I look at the data that's done by a government entity that says, like, here's the safety record of these vehicles. So every time a car is built, it has a safety record, and you can see cars moving up and down those stacks. And so when there's data behind the safety of it, then why wouldn't you trust it? Another person said, well, I'd feel better if we started out like in the country doing it, because there isn't as many unpredictable things that happen maybe out there. And then another person said, well, I don't know how you're going to convince me that somebody's not going to hack into these things. But cybersecurity is another big research effort that's in this. And we have obviously lots of cybersecurity experience working with the Department of Defense, and our job is going to start to develop these working groups where we could bring this community that hasn't had to be concerned with cybersecurity on the vehicle or the networks, the security of the networks, and it's going to be an Internet of Things connectivity, and educate everybody that how important that is and how to do it. It's not that we don't know how to do it; we just have to tell a new community how to do it.
So I've got Ethan, whose major is physics, from Minnesota State University at Moorhead. We're wondering why drones have 4 or more rotors, but commercial craft like helicopters have less, like 2. What are the advantages and disadvantages of more rotors or less?
Well, it gives the vehicle more flexibility of movement. And so the types of operations that these companies are trying to go forward with using these small UAS, that's what's going to be needed, is that kind of that flexibility and dynamic nature to how these vehicles can be controlled. And so they need to be very accurate and kind of turn on a dime, be able to kind of navigate these urban environments. And so having more rotors in the types of configurations that we have and that we're seeing with these vehicles that we participate with, they really get towards enabling the types of use cases that a lot of these companies want.
I see. So I've got Ryan, whose major is aerospace engineering from The Ohio State University. Are there further plans to continue to roll out more, you said Lance-like services, or will only private industry be driving it? Services like this could go a long way towards introducing the public to UTM, to the UTM concept.
Yeah, so like I was mentioning before, so Lance is this system right now it stands for Low Altitude Authorization and Notification Capability. And so it's a service that allows operators that want to fly a vehicle close to an airport where before you need to go through a lengthy paper process and kind of negotiate with the facility that you want it to operate near. But now you have this service, Lance, that like streamlines that whole thing. So the operator...
It's developed by the FAA, so
Right. But it came from NASA. So NASA, as part of our initial architecture and kind of a key piece of it is this UAS server supplier, which is going to be that piece that supports all the operators and their operations. And so that's really like the extension of where Lance is. And USSs are going to be the thing that kind of supports all the communication between all the airspace users. That information exchange is facilitated by the USSs, and so this is really the next step for this kind of system, the ecosystem, to really to take shape is through that piece. So you can consider that a Lance-like capability, although at NASA we think USS came first, and then Lance came, or is a descendant of what we've done so far.
So I've got another one from Hamza at Georgia Tech. How do these urban drones perform in the case of loss of GPS? Do you have terrain identification systems for navigation, or do you have to have terrain identification systems?
So,
what would you do in UTM?
Yeah, so for UTM, that was one of the contingency cases that we were looking at, starting back in TCL 2, 3, and really in TCL 4, where we're in this urban environment and you're you're more likely to run into situations where you might lose navigation in the kind of urban environment where you have buildings and other kind of impacts to communication and navigation. And so, one of the things we're looking at is how do you have redundant systems that can kind of compensate for when you lose your navigation, your initial primary navigation feed. Also looking at contingency procedures. So how do you land or recover safely in this type of environment? And this gets at kind of what we were looking at even across those TCLs where, the idea is in order to even access kind of an urban type of environment, you may have to provide extra equipage and capabilities and be able to demonstrate as part of to get an authorization to operate in that type of environment. You have to show that your vehicle and your capabilities are commensurate with the complexity of that type of environment, which includes like loss of GPS and lost comms and other cases as well.
And other pieces. I have a question here from Kabid in biomedical engineering, who is actually writing in from India, from the National Institute of Technology, Raipur in India. How do you quantify the perception of aviation noise from a human subject? Are there any applications of artificial intelligence in the field of aeroacoustics?
So we have been talking to some people that have a military background of how they come up with dynamic routing and change it just slightly so you're not wearing out like the carpet in the main walkway of the house, right? So each time you do a flight plan, it's not always right on the same spot, but there are tweak and variabilities of who you affect. So it's kind of a scattering. It's one idea so you could, you could certainly use artificial intelligence for something like that. But there is that whole where you're going to point it. So if you had a heat map of the city, of density populations, then you should be able to be reading that and pointing noise, however you do that with torque your propellers, or people have different ideas. It just slight banking or something. But yeah, I definitely that could play a role.
Well, that's all the questions that we have, but I want to thank you, Star and Jeff, for your work, your insight, and especially for your advice to all the students joining us this evening. Before we sign off, I do want to share some key resources and opportunities with our audience. This webinar has been recorded and it'll be available on the series website. There is a slide where you can learn more, and so be sure to visit this section of the website. You'll find technical papers that our subject matter experts recommended and information on a wide range of student and faculty opportunities through NASA and the Space Grant Program. The Connect with Space Grant slide, this next one, has a link for you to connect with the NASA Space Grant Program in your state so that you can learn more about scholarships, fellowships, internships, the student flight and design programs, faculty research, curriculum projects, pre-college enrichment programs for our students and teachers. Space grants are a key link to NASA in each state, so do explore the website and connect with your program in your state, the District of Columbia, or Puerto Rico. NASA offers paid internships at the agency's 10 centers through the NASA Internships and Fellowships program, as well as fellowships for graduate students. We heard about those tonight. The program website offers more information on these programs and how to apply. NASA's internships and fellowships are open to U.S. citizens. And NASA Aeronautics offers a special opportunity called the University Leadership Initiative. It's different from other research grants because they fund teams led by universities that get to propose what they want to research. After 2 rounds of awards, NASA's engaged with 34 universities so far. The key is that the universities lead, as long as the topic is related to NASA's work. So far, solicitations go out annually via Inspire's NASA's online system. On Wednesday, November 6th, we're going to close out this series this year with a look at electrified aircraft, tackling the challenges of alternative propulsion. Please join us. The host next time is going to be Steve Ruffin. He's the director of the Georgia Space Grant Consortium and a professor and associate chair of aerospace engineering at the Georgia Institute of Technology. So, on behalf of the NASA Space Grant Program and NASA Aeronautics, thank you for joining us tonight.